Now let's look at an example of how we would design a pressure vessel. So with pressure vessels, there are assumptions for solving the problem if the problem has thin walls or thick walls. In this case, we are solving for the thickness, so we'll have to check for that after we are done. So what I typically would do here in this case is solve for the thickness using our thin wall assumptions, and then check if the ratio between the radius of the tank and the thickness would hold true. So we see this tank and we're trying to figure out the thickness for it. It's a pressurized cylinder with hemisphere end caps, and the inside diameter is 24 inches, the length is 72 inches, and we need a safety factor of 3 against yielding. We're going to assume that the tank is made from this 1040 hot rolled steel with a yield strength of 42 kpsi and has an internal pressure of 150 psi. So you'll see a few different equations for our tangential stress for a thin-walled cylinder with internal pressure. So quite often we just assume that the stress distribution in the walls is going to be even across the whole thing. The average tangential stress is going to be equal to Pi times the radius over T. That's not the actual maximum, but it's very close. And so often we just go with this assumption because you will also see that like in the Shigley book, for example, that we would have the pressure is equal to the inside diameter plus the thickness all over 2T. And this is very close to that first equation with the average stress. So quite often when we're doing a pressure vessel, we usually have a higher safety factor, so we're fairly safe using this average tangential stress, and that's what I'm going to use here in this case. If we're going to be able to solve for our thickness, we need to understand what our allowable stress is. In this case, our allowable stress is going to be our yield strength divided by the safety factor, which is going to be 42 kpsi divided by 3, which ends up being 14 kpsi. So with that value, we can substitute that 14 kpsi in for our tangential stress in the thin wall equation at the top. And so we would have 14 times 10 to the third psi is going to be equal to our internal pressure of 150 times the inside radius, which is 12 inches, all over our thickness. Then if we rearrange that, we would have that the thickness is going to be equal to 150 times 12 all over our yield strength divided by the safety factor, which is that 14 kpsi. And from that we would get that our wall thickness would be 0.13 inches. And now we need to check that our assumption to use the thin wall equations is valid. So this is done with the relationship and the assumption that our wall thickness is less than our radius over 10, or our radius needs to be more than 10 times our wall thickness. So in this case, we would have 0.13 is less than 12 divided by 10. So we see that our assumption to use the thin wall equations is valid. So my process for pressure vessel problems. Understand what dimension we're solving for, or what variable we're solving for. We might be solving for the wall thickness or the radius. We might also be solving for what pressure could we pressurize this tank to. Then I will find the allowable stress with our safety factor. And if I'm not sure if I can use thin wall or thick wall assumptions, I will solve using thin wall. Then once I solve it, I will check the thin wall assumptions. So that I make sure that solving using the thick wall or the thin wall assumptions is a valid choice. And from there, I can double check my work and I can be done with this pressure vessel problem or pressure vessel design case.